Now we're going to move into Vasicek delta and Vasicek gamma. So here I'm going to give you the formulas and then we're going to turn into examples. This is the formula for Vasicek delta. At time t equals 0, we can determine the Vasicek delta with the prices of the bond in the up and down scenario and the interest rate in the up and down scenario. An interesting feature is that this interest rate is the short rate. It's always going to be the short rate. And the Vasicek delta is going to be minus B plus minus B minus over R plus minus R minus. Interpretation is going to be identical than what we had before, which is that a minus change in the bond price when short rate increases by 100 basis points is what's going to approximate the bond price change. Now, here you need to quote R's as 10 percentage points, so 10 and not 0.1. And for gamma, you're going to need to compute the delta in the up scenario and the delta in the down scenario so that you can compute gamma as minus delta plus minus delta minus over R plus minus R minus. And interpretation is just going to be like dollar gamma, which measures how delta is affected when interest rates change. Now we're going to use again the tree that we constructed at first, the one with the local expectation hypothesis. So the tree looks like this, and the first exercise to understand the delta Vasicek and the gamma Vasicek is to compute delta Vasicek for 0 coupon bonds that have a face value of 1 and that expire in t equals 1, 2, and 3 years. So the first one is going to be delta Vasicek of the 1 year. And if we follow the formula, it's going to be minus and then bond up. So we know that 1D1, the value of a 1 euro bond in 1 year is going to be equal to 1. And same thing here in the up and down scenario. So this is going to be 1 minus 1. And now the rates that we're going to take are the 9.67 minus the 4.33. And these are not going to change. Still, we know that this is going to be equal to 0. Now, delta Vasicek for the 2 year is going to be equal to minus, and then we need to take the price of a 2-year bond in year 1. So this is going to be e to the minus 9.67% times 1. Even though it's a 2-year bond, since we're pricing it at year 1, 1 year has already gone by, e to the minus 4.33% times 1 again, and this over, so this would be plus the minuses here, over, and again, we're going to take this quantity. So we take exactly the same rates, even though this is being computed for the 2-year bond. So this is going to be 967 minus 4.33, and we're going to get 0.009325. Finally, the delta Vasicek over the 3-year bond is going to be equal to minus e to the minus 9.25% times 2 minus e to the minus 4.50 times 2 over, and then again, we once again use exactly the same denominator. So this would be the 967 minus 4.33. What's the reason behind that? That we're interested in how the short rate affects the prices. So the short rate in this case is the 967 and the 4.33. And here we get 0.015511. The next question that we're going to solve is what's the value and the delta dollar of a 3-year coupon bond that's going to pay annual coupons of $10 and is going to have a face value of 100. So this bond is going to pay in years 1, 2, and 3, and the payments are going to be of 10, 10, and 110. So if we have the discount factors D1, D2, and D3, then the present value of each one of these payments is going to be 10 D1, 10 D2, and 110 D3. So this means that the price of this 3-year coupon bond is going to be equal to 107.9026. This is by adding this 3 values here. For example, 1D1, it's going to be equal to e to the minus 7%, and this one is going to be equal to e to the minus 6.87% times 2, and the third one e to the minus 6.74% times 3. As for the delta Vasicek, it's going to be equal to the number of units of the 1-year bond times the delta Vasicek of the 1-year bond plus the number of units of the 2-year 0 coupon bond times the delta Vasicek of the 2-year 0 coupon bond. and number of units of the 3-year bond times delta Vasicek of the 3-year bond. And this is equal to 10 times 0 plus 10 times 0.009325 plus 110 times 0.015511. And this is equal to 1.79946. The third question is, what are the gamma Vasicek of the 1, 2, and 3-year zero coupon bonds? So the gamma Vasicek of the 1-year bond is going to be equal to 0. Why? Well, because this is minus delta plus minus delta minus. We're going to see in a second what that is, R plus minus R minus. Now, what this means is in the up scenario, I need to compute delta plus. To compute this delta plus, I need the following scenario. Now, because this is a 1-year bond, this 1-year bond doesn't even have a price beyond this, so it's not going to change in price. It's not even going to be affected. So this means that delta plus and delta minus in this case both are 0. So that's why this is equal to 0. Now let's turn into the gamma Vasicek for the 2-year bond. And this is going to be, I'm going to have to compute the delta plus and the delta minus. So delta plus is going to be the value of a 2-year bond in 2 years. This is 0, 1, and 2 years. So we know that in 2 years, a 2-year bond is going to have a price of 1 in the up scenario and 1 in the down scenario. And same is going to happen for the delta minus Vasicek. So all these prices are going to be equal to 1. That means that the delta plus and the delta minus both are going to be equal to 0. Why? Well, because interest rates are going to change, but they're not going to affect the price of our 2-year bond. So this one is also going to be 0. Now, the one that is going to be interesting is the gamma Vasicek of the 3-year bond. So this one, we have to compute first the delta plus of the 3-year bond. So let's see what the delta plus is. To compute the delta plus of the 3-year bond, we need the short rate, the one that goes from 2 to 3 in the up scenario and 2 to 3 in the down scenario. So the delta plus is going to be e to the minus 12.34% minus e to the minus 7% over the change in rates. So it's going to be the 1234 minus 7. And this is equal to 0.009079. And for the delta minus, we apply the same logic that we applied before, but now instead of the 1234 and 7, we're going to use 7 and the 1.66, and we're going to get that this is going to be equal to e to the minus 7% minus e to the minus 1.66% over 7 minus 1.66. So this is equal to 0.009577. Finally, we're able to compute the gamma Vasicek for the 3-year bond, and it's going to be equal to minus, and then the delta plus of the 3-year minus delta minus over R plus minus R minus. This is going to be equal to minus 0.009079 minus 0.009577 over 9.67 minus 4.33. And this is going to be equal to a very small number, 0.0000 and then 93.2615. Now let's turn into the last problem, which is balance sheet and immunization. So imagine that you have liability of 300 units of the 3-year coupon bearing bond that we priced before, the one with the $10 coupon. And then we have also net equity of $60,000 in cash. And now we need to use the zero coupon bonds that we have and all cash to restructure the balance sheet to achieve a delta Vasicek equal to 0. So the net equity, it's equal to $60,000. Liabilities, we have 300 units of the 3-year coupon bond. So it's 300 times 107.9. You go and take all the digits, and that's going to give you 32,370.78. And then if we add this 2, we're going to obtain the assets, which are equal to 92,370.78. So now we're going to use the 1 and 2-year zero coupon bonds to immunize. So now we have to set up our 2 equations with 2 unknowns. So the first one is going to be for the value of net equities, the second one for the delta Vasicek of the net equities. Let's see what those equations are. The value of net equities is 60,000, and this has to be equal to number of units of the first bond times the price of that zero coupon bond, which is 0D1, plus the number of units of the 2-year bond times the 0D2 minus liabilities, which the value is 32,370.78. Now the delta of net equity that we want to achieve is 0. and this is going to be equal to N1 delta Vasicek of the 1-year bond plus N2 delta Vasicek of the 2-year bond minus 300 times the delta Vasicek of the 3-year coupon bond. Let's write these equations with more numbers. 60,000 equals N1e to the minus 7% plus N2e to the minus 6.87% minus the 370.78. 0 equals N1 times 0, since the delta Vasicek of the 1-year bond is 0, plus N2 times 0.009325 minus the 300 times the 1.7994. We solve and we find that N1 is going to be equal to 44,950.239 and N2 is equal to 57,891.47. So at time t equals 0, we're going to have liabilities for 32,370, the net equity for 60,000, but now we bought 1 year and 2 year zero coupon bonds. These are the quantities, and the total adds up to 92,370. Now let's see what happens in the up and down scenarios. And then now we're going to move to t equals 1. So the assets, I'm still going to have the same number of 1 year zero coupon bonds and the same number of 2 year zero coupon bonds. Now, the 1 year zero coupon bonds expire here and their price is 1. So it's the 44,950 units times 1. And now the 2 year zero coupon bond is now a 1 year zero coupon bond that I need to discount at the 1R2 rate, which is 9.67. And this adds up to 97,505. Now, the liabilities are now like 3 bonds. So it's the zero coupon bond that I paid, that pays my $10. So I'm receiving my $10 plus the 300 units times the $10 that I'm going to receive 1 year later in year 2, which is E to the minus 9.67% plus the 300 times the 110 E to the minus 9.2% times 2. I'm going to write the net equity further down. This is equal to 33,149.9. So the value of net equity is the future value of 60,000, which is going to be equal to 64,355, or it's going to be the subtraction of the 97 and the 33,000. Now we do exactly the same thing for the down scenario. So this is times 1, this is times E to the minus 4.33%, and then we get here 100,388.51. And for the liabilities, now we're going to get the 300 times 10 plus 300 or 3,000 times E to the minus 4.33% plus 300 times 110 E to the minus 4.5% times 2, and then we obtain that this is equal to 36,032.6, and then the value of net equity is going to be still the same value, 64,355. So this is how you do the immunization using the delta Vasicek for different types of securities. And we will apply this in future chapters when we compute delta Vasicek for derivatives. Some extra notes on delta and gamma Vasicek. The first one is delta Vasicek is different, and this is very important to the delta dollar we computed before. Some people get very confused at some point when I ask delta. They still compute this delta here, and you have to watch out because sometimes I'm going to compute delta dollar, sometimes I'm going to compute delta Vasicek, and they are different. Same thing for the gamma Vasicek. Finally, for small h, when h tends to 0, delta Vasicek can be approximated with this formula that depends on the mean reversion parameter and the discount factors. This is what we did to compute delta and gamma Vasicek for portfolios. We added the quantities plus the delta or the gamma Vasicek of the different components. Note that the ends can be negative. So let's conclude this chapter. We introduced a more realistic short-term binomial tree that included fudge factors. We learned how to get the term structure for each node. We learned how to compute bond prices and sensitivities of bond prices under the binomial tree that uses the Vasicek model. And finally, we learned how to do risk management for, in this case, bonds, but in general, we're going to be able to do it for derivatives. Thanks for watching.